So the first question is a pretty quick one here, which is that there's 52 cards in the deck, and we can see that in the image because there's 4 different suits, and there's 13 cards in each suit. So 4 times 13 is 52. So if I want to know the probability of pulling a heart, so probability of pulling a heart, I'm going to put an H for heart. I know that there are 13 total hearts out of the 52 total cards. And if I simplify that, that would be 1/4, or I have a 25% chance of pulling a heart. Now, if I move on to the next one, which was what's the probability of pulling a face card if I draw one card? Well, probability of a face card, I got to think about, well, there's a Jack, King, Queen for each suit. So there's 3 face cards in each suit, and there's 4. So we got 3 faces times the 4 suits out of the 52 cards, which means that I have 12 total cards out of the 52 that would work. And if I simplify 12 out of 52, this gets me to 3/13, which is about 23.1%. Now, the next question asks, I put $2 into my game, and I want to know what's it going to be. If I pull a face card, I get $10. What's my expected value to win? So I know that when I talk about expected value, I can do it a couple different ways, but one way is that I can take my probability of pulling a face card, multiply it by the amount that I expect to win. So I'm going to put just a $sign here, and then I'm going to subtract out what's the cost to play. So the probability of face card, we said just a second ago, was 3/13. We said that you could win $10 from that. And the cost to play is right here. I put $2 towards the game. So if I go through and I simplify my expression here, I get about 308 thousandths, or that's 31 cents. So if I play this game for a very long time, over time I would expect to win 31 cents. That doesn't mean I'm going to win 31 cents when I play the game, because think about it, I'm either going to win $10 or lose $2 every time I play. So it's this long-term projection that I would expect to come out a little bit in the positive, just on around 31 cents. So now we start to look at some more complex types of problems, then start looking at drawing multiple cards. So the first thing I ask, is drawing 2 cards independent or dependent? This is dependent, because once I pull the first card, I have 52 options for that first card. So I'm going to put card 1. But when I get to card 2, so if I think about pulling them one at a time, I flip the first card, lay it down. Well, how many cards are left for me to choose from for card 2? There's only 51 cards. So I no longer have the same sample space once I take out that first card. And that's the important thing to recognize here. So when I talk about in this next problem about pulling 2 jacks, I have to think about it as, what's the probability that I pull a jack on the first one and a jack on the second one? So when we look at that, how it's written more formally, we'd say probability of jack times, because it's an and problem, a jack on the second, given I got a jack on the first. So let's look at what that means. So how many jacks are there in the cards? Well, I could look through and make sure, but there's 1 jack for every suit. So there's 4 total jacks out of the 52 cards. Now, when I get to my second one here, what's the probability of getting a jack, given that I just pulled a jack? Well, I know, as I just said, I pulled a jack, so I'm down to 51 cards. Well, how many jacks are now left in my deck if I'm assuming that the first one pulled out was a jack? Well, that only leaves me 3 more jacks left in here, which means that I'm now down to having a 12 out of 2,652, which can simplify to 1 over 221, and that's about just under 1/2 of 1%. So under 1/2 of 1% would I expect this to potentially happen. Now then they ask the question of what's the probability of pulling no jacks, 0 jacks total. And so here I have the probability of no jack, I'm going to put NJ, no jack on 1, and no jack on 2. So just like before, we say, well, that's the probability that I don't get a jack on my first one, times, because of that and right there, I don't get a jack on the second one, and I'm going to take into consideration that I didn't get a jack on the first one. That's what that little line there means, like a given. So how many cards, if there's 4 cards that are jacks, that means there has to be 48 cards that are not jacks. Now when I go to my second situation, I assume I've pulled a card out. That's the whole point. I pulled one card out, so I now only have 51 cards left. And the one I pulled out, I'm assuming was not a jack, which means there's now only 47 cards left that are like that. And if I multiply across here, I'm going to end up with 2,256 out of 2652, which simplifies down to 188 221st, or about 85.1%. So a much, much more likely occurrence. Now, if you think about it, the last one was 0.5%. This one's 85%. That doesn't add up to 100%. Well, that's because there's also the chance that maybe I draw only one jack, or maybe I draw, and that's where my other thing, draw a jack on the first one, or I draw a jack on the second one. So those probabilities haven't been taken into consideration. So that's why I don't add up to 100% yet. So now I need to find my expected value of this new game where if I pull 2 jacks, I win $100. If I pull 0 jacks, I win $2, and it costs $5 to play. So I take each of these expected values, and I'm going to multiply them by their chance of winning, and then I subtract out my chance to play. So I start with the first one. My chance of pulling 2 jacks I found to be 1 out of 221. And if that happens, I win $100. But I got more than one way I could win. I could also win by doing 0 jacks, which we just found to be 188 out of 221. And if that's the case, I win $2. Now it does cost to play, so I have to subtract out the $5 it costs me to play this game. Now, if I simplify and multiply across, I end up with something around -2 and 846 thousandths, or about -$2.85. That means I'm expected to lose about $2.85 if I play this game for a very long time. So that's what expected value can help us do. It can help us understand when are we going to win and when can we look to actually lose money. And this would be a losing game. Now we get to our final questions here, looking at the idea of, well, let's take it to another level, which is where I want to pull all 4 jacks. So that would be that I'm going to pull probability of a jack on the first, and a jack on the second, and a jack on the third, and a jack on the fourth. So if I think about what that means, it means I'm going to get the probability of a jack on my first one times the probability that I get a jack on the second, given I got a jack on my first one, times the probability that I get a jack on the third one, given that I got jack 1 and jack 2, times the probability that I get the jack on the fourth one, given that I got Jack 3, Jack 2, and Jack 1. Now, as we said before, we know this one's 4 out of 52. So now when I get to the next one, I'm like, oh, I took out a card. So I'm now down to 51 cards. Well, I'm assuming it was a Jack. So that means there's only 3 Jacks left. Now, I take out another card. So now I'm down to only 50 cards. And I assume that those first 2 were my Jacks, which means I only have 2 Jacks left. And when I get to my last one here, I've taken out yet another card. So I'm down to 49. And there's only 1 Jack left to choose. And if I simplify this, I'm going to get 1 out of 270,725. That's a very, very small chance of winning. Now, the second problem here asks, what's the probability of me breaking even? In other words, I don't make money or lose money, or I'm looking at the idea of my expected value equaling 0. So if I think about just setting up my equation, I know that my expected value I want to be 0. I know my probability is 1 out of 270,725. I don't know how much the game needs to pay out, but I know it costs me $1 to play. So if I think about this, this would be 1 equals the 1 times 270,725 would be x over 270,725. So if I want to get x by itself, I need to multiply both sides by 270,725. And that means that the value I would have to win would have to be $270,725.